The approach of the previous section was easy to explain, but somewhat cumbersome to use in practice. In this section, we consider an approach that is way easier to use in practice, but perhaps a bit more complex to explain. To cut down on the work we need to do when applying the method, we should allow only to assign predicates to some of the nodes in the program graph. This gives rise to the notion of a partial predicate assignment. Let us take a look at the factorial program once again. A partial predicate assignment does not need to express predicates for all the nodes of the program graph, and here we have avoided specifying predicates at the nodes Q2 and Q3. The remaining predicates are as they were in the last section. The only requirement we have is that we specify a predicate for the initial node and for the final node, and one node for each loop in the program. We say that these nodes cover the program graph. For the factorial program, we use Q1 for the loop. To explain what it means for a partial predicate assignment to be correct, we first need the notion of a short path fragment. This is the shortest possible path from a node with a predicate to another node with a predicate. Hence, there are no predicates assigned to any interior nodes. For the program we are looking at, there will be three short path fragments. One from the initial node to Q1, one from Q1 through the loop to Q1, and one from Q1 to the final node. We collect the set of actions on the short path fragment. What does it mean for a partial predicate assignment to be correct? We need to consider each short path fragment and ensure that whenever a concrete memory and a virtual memory satisfies a predicate at the start of a short path fragment, then the modified concrete memory and the same virtual memory also satisfy the predicate at the end of the shortest path fragment. It is time for you to try this out on the factorial program using the short path fragments displayed. The online system supports partial predicate assignments. You must choose the environment verification conditions. You can ask the system to produce a set of covering nodes that live up to our requirements. You can then write predicates in plain text that should hold at these nodes. You can then ask the system to produce the proof obligations, and it will construct the short path fragments. It will leave you to check correctness, as unfortunately there is no automatic support for this. So let's see how this works out on a more complex example. Let's consider insertion sort once again. For the four covering nodes produced by the system, you must supply the required predicates. The ones for the initial and final nodes we already discussed. You will have to work out the ones for the two additional nodes. You may use sorted, permuted, and almost as defined here as needed. Finally, you should generate the short path fragments and consider each one in turn, showing that indeed they are correct. In fact, it would be possible to get rid of one of the nodes and still live up to our requirements. Can you figure out which one?